So chapter 3 is going to be applications of derivatives. And the first application is we're taking a look at extrema on an interval. So let me talk about what I mean by that. So definition of extrema. And I don't want to belabor this point too much because if you've printed off the notes, you should just be filling in a few blanks. There's quite a bit of writing on this first page. So we're going to let f be defined on an interval I containing c. I'll draw you a picture in a moment. F of c is the minimum of f on I if it's the smallest value on that interval I, and it's the maximum if it's the largest value. The maximum and minimum values are called extreme values, or extrema, of the function on the interval. They're also sometimes called absolute maximum, absolute minimum, or global maximum and global minimum. So let me draw you a picture of what this looks like. Okay, so this is telling us that we have an interval that starts and stops somewhere. So this is my starting spot, this is my stopping spot. That's what this is telling you. It's telling you there is a location somewhere here that is the biggest y value. And I suspect that you can see it's right here, right? This one is my absolute max. And it happens to occur on an end point. Now, the absolute min does not. The absolute min is right here, and it occurs on sort of a valley location. So this is my absolute min. But whether it occurs on an endpoint or whether it occurs at a peak or a valley, it will occur because the interval is closed. It starts and it stops somewhere, so it has to have a biggest y value and a smallest y value. Okay? Take a picture real quick if you didn't get it all written down, because I'm going to switch slides. You can fill in the rest of those pieces a little bit later. So when I'm telling you that it has to have one of these things, that's actually what the extreme value theorem says. If f is continuous, okay, so no jumps, no asymptotes, no holes, on the closed interval, it will have both a maximum and a minimum on the interval. Has to happen. Did you not get the picture taken?
No, I took a picture as mainly after you switched slides.
Okay, do you want to take it real quick?
Please.
Do it again. You're okay.
Thank you. I got it.
Okay. So we have another type of extrema, descriptively. It's called a relative or a local extrema. This means that it's the biggest value or the smallest value in a nearby area. So picture-wise, what this is actually telling us is, let's say we had a graph that did like this. It continues on up here and it continues on down here forever. The interval does not necessarily even have to be closed. If this graph goes on forever, its maximum and its minimum are actually like infinity and negative infinity, right? It continues up forever, it continues down forever. But it has some spots that have some of those features of the absolute maximum before. This one would be called a relative max. Or they're sometimes called local max. And this one would be called a relative min. And what it's actually saying is that if you looked in a nearby area around these points, they're the biggest, they're the smallest in that little area. So it'd be like doing this. If everybody stood up, you don't need to stand up, but if everybody stood up right now and we put us in height order from shortest to tallest, somebody is the shortest. It may be me, especially with all you guys in here. It's not, because I think I'm taller than Grace. It may be that there's two people that are the exact same height too, right? I mean, you could have two people that are coinciding, they're both the shortest. And the same thing for the tallest. There's somebody who is the tallest, but you're probably not the shortest or the tallest person on campus, correct? Probably not. You might be, but you wouldn't have to be. But in this relative area of discussion right now, you are the shortest or you are the tallest. Does that make sense? That's what's going on this picture. And so we'll stop right there for today.